Okay, in last class we had discussed about balancing of rotating masses, and with an introduction started with an first case, that is balancing of a single rotating mass by a single mass rotating in the same plane. Okay, so this we had seen in the last class where we saw that a counterbalance can be added there opposite to that, and Fc1 and Fc2 should be equal, and we get the conditions for masses in a single plane. So next we will see balancing of a single rotating mass by two masses rotating in different planes. Okay, so if different planes are there, in that how this balancing can be done. So here introducing a single balancing mass in a same plane of rotation as of that of disturbing mass, and the centrifugal forces are actually balanced here. So in other words, the two forces are actually equal in magnitude and opposite in direction. So but this type of arrangement for balancing will give rise to the couple. So last class we have seen the balancing where you are used only the uh, this in the same plane. So there was no direction for the taking the couple. So here, as the plane is being shifted to another plane, so we need to consider here the couple also. So the arrangement you will see in the, so the couple which tends to rock the shafts in the bearing, and therefore now to balance it completely. So two balancing masses are actually placed in two different planes that is parallel to the plane of the rotation of the disturbing mass, and from this there are two conditions which will be to be satisfied. One is the net dynamic force acting on the shaft, which is to be equal to 0, and this requires the line of action of the three centrifugal forces must lie in the same plane there, and here the nothing but the center of masses of the system must lie in the axis of rotation. So this is the condition for static balancing. And one more condition is about the net couple due to the dynamic force acting on the shafts should be equal to 0. So in other words, the algebraic sum of the moments about any point must be equal to 0. So this condition 1 and 2 together, that will give the dynamic balancing, and two possibilities may arise, that is the plane of a disturbing mass may be in between the plane of the two balancing masses, or it may be the condition where the plane of the disturbing mass may lie on the left or right of the planes. So both cases we will see now. So first case, when the plane of the disturbing mass lies in between the plane of the two balancing masses. Okay, so you can see in the figure. So in this figure you can see there is a disturbing mass m at the center, you can see. So the disturbing mass shaded portion, which is having the ball having the shaded with the hatched lines. Okay, so that part is a disturbing mass there, and you can see that is given by plane A, that is center, you can see given by plane A, and this is to be balanced by two rotating masses, that is m1 and m2. So you can see m1 and m2 are in different planes. For example, you can see the m1 mass having the plane of L there, the left side. On the right side you can see there is a one more plane, that is plane M. So there you can see that it is connected with mass m2 there. Okay, so two different planes you can see on L and M, and let the radius for the center part, that is let us take it as a normal r, then here as r1 and r2 radius for the respective from A, L and M. Okay, so center part will take an r radius r, and the left side will take r1, and then right side will take it as r2. Similarly, the length, that is L1 be the distance between the planes A and L. So you can see the distance here shown in the figure. So left side L1, and the right side we take it as distance from A to M, we take it as L2. Okay, and the total distance between L and M we take it as L. Okay, so from this we need to understand how the balancing can be done. So just make the figure make it more understandable. So just try to understand the figure, that is main important. So center will be the disturbing mass and other two will be balanced now. So in the figure you can see the side view also given there. So balancing of single rotating mass by two rotating masses in different planes. Okay, when the plane of single mass lies in between the planes of two balancing masses. So let us see the equations. So the first one at the center. So Fc is equal to m omega square r. So that you know. So for the center we get Fc equal to m omega
Sir,
square
is
into
there a
r.
pendulum?
Hello.
Sir, is it a pendulum or what's that figure?
Hey, why pendulum, man? This is balancing of masses. We are
Hello,
discussing
sir.
of balancing of mass in the last class. Last class you are there?
Yes, yes,
Huh?
yes, sir.
So last class we discussed, no, that
Yes, sir.
this is mass. So whenever disturbing mass is there like this was in the same plane. Okay, now we are considering for different planes. Okay, mass is rotating in this plane. So how balancing can be done for different planes that we are seeing now. Okay, so for the center part, we get Fc equal to m omega square r. Same way for the plane L, we get Fc1 is equal to m1 omega square into r1. So here you can see this one for L. Similarly for plane M, we consider for mass 2, that is M2, and here so here Fc1 for M1 plane, that will get M1 omega square into R1, and Fc2 will be M2 omega square into R2. So since the net force acting on the shaft must be equal to 0, so therefore the centrifugal force on the disturbing mass must be equal to the sum of the centrifugal forces on the balancing part, because you are going to balance this center part with the two masses that is disturbing at M1 and M2. Okay, so here the centrifugal force for the center part, what you're going to balance, should be equal to sum of the other two. So that we are considered here. So Fc1, Fc should be equal to Fc1 plus Fc2. So that conditions, let us substitute the values of Fc, Fc1 and Fc2. So we get m omega square into r equal to m1 omega square into r1 plus m2 omega square into r2. So omega square all get cancelled. So left out with m into r will be equal to m1 into r1 plus m2 into r2. So this is the first equation what we will be getting. Okay. Now let us take the next part, that is now in order to calculate the magnitude of the balancing force at the plane L, that is or the dynamic force on the at the bearing Q of the shaft. So you have to take the moments about point P. So which is the point of intersection of the plane M and axis of rotation. So this you have to consider now. So let us take the distance by taking the couple also. So you can see at this point L there is a point Q, and for M there is a point P there on this plane L and M. Okay, so on these points let us take the couple. So first condition will be getting Fc1 into L will be equal to Fc into L2. So Fc1 into L. Okay, so the first one Fc1 into L, so that will be equal to Fc into L2. If you substitute this one now, so you get m1 into omega square into r1 Fc1, then that will equal into L equal to Fc1, that is m into omega square into r into L2. Okay, so substituting this, omega square get cancelled, so we left out with m1 into r1 into L, that is equal to m into r into L2. So therefore we will be getting just sending L that side to the denominator. So we get m into that m1 into r1 equal to m into r into L2 by L1. So this condition will be getting, that is equation number 2. Next, similarly, in order to find the balancing force in plane M, that is the dynamic force at the bearing P of the shaft, you have to take the moments about Q. which is the point of intersection of the plane L. So this is now the second we're taking for the plane L now, that is at point Q. So in taking this condition, so you get Fc2 into L is equal to Fc into L1 now. So taking the same conditions, m2 into omega square into r2, substituting Fc2 value and Fc value here. So omega square get cancelled. So we left out with m2 into r2 into L1, L equal to m into r into L1. So finally we get m2 into r2 equal to m into r into L1 by L. So we get equation 3. So it may be noted that equation 1 represents the condition for static balancing, that is first case, and but in the dynamic balancing you have to achieve second and third condition also. Okay, so in all the conditions are satisfied, it becomes dynamic balancing also. So same way we take the second case now. Here when the plane of disturbing mass lies on one end of the planes of the balancing masses, okay, that is you can see now the disturbing mass at the one side on the left side and other two masses on just beside that. Okay, so in the first case we have taken the same mass, so disturbing mass was at the center. Now we can see it on the other side. Okay, so in this case the mass is now taken as the plane, same thing, plane A, we take the same name but on the left side, and the planes L and M are shown in this figure, that is on the right side of this disturbing mass, that is M1 and M2 you can see, and automatically the distances will be taken the same way, L1 here, then L here, total length from L to L M, and then same we take L2 distance. So just the position changes. So here if we want to get now condition for the system to be balanced, so here Fc plus Fc2, okay, Fc plus Fc2 should be equal to Fc1. So in this condition you have to achieve. So here substitute the values, m into omega square into r, Fc value and Fc2 value and Fc1 value substitute. So we'll have you get the equation as m into r plus m2 into r2 equal to m1 into r1. So equation 4, let us take equation 4 for this. And the same way if you take the couple, so same way how we got the previous condition here for couple, same way we'll be getting here to find the balancing force of the plane L at bearing Q or shaft. So you have to take the moments about P. So we get Fc1 into L equal to Fc into L2. So substituting the value of Fc1 and Fc, again we get the same equation as of equation number 2. So equation 2 and 4 are nothing but same, you can see, that is m1 into r1 equal to m into r into L2 by L1. Next part, that is taking the balancing, finding the balancing of force of the plane M. So that is dynamic force around by bearing P of the shaft. So you get same equation that of equation number 3, what you have considered here, same equation you're getting. So here also, so you get m2 into r2 equal to m into r into L1 by L. So either you take any planes, either shift on the center or the left side or right side, the equation remains same. So that is being shown here. So getting same equation here, that is 2 and 4 are same and the 3 and 5 are same. Okay, so you have considered both the conditions. Okay, so to balance two masses in different planes, you need to use these conditions. Okay, so next condition we'll see about balancing of several masses rotating in the same plane. Okay, so you can see in the figure, so there are several masses rotating in the same plane, and you have to find out the counterbalance so that the entire system is balanced. Okay, so here you can see take a number of masses, for example say 4. So you have taken 4 masses, that is m1, m2, m3 and m4. So let us see this figure. So we're getting the different masses at different plane. So for this actually we can go for two methods. One is analytical method, one is graphical method. Okay, so the problems what you're going to get in the exam, that will be based on masses in the many masses in the same plane or in different planes. Okay, so first two conditions just for your understanding, but the main thing you want to follow this now. Okay,